So this is the last example in this topic. Find the area of the surface generated by rotating So let me break this suspense. Rotating what? Rotating y equals e to the x, where x is a value between 0 and 1. And let's rotate it back about the x-axis. So, sketch. Y equals e to the x. We are well familiar with this function. When x equals 0, y equals 1. When x equals 1, y equals e to the 1, or 2.718, something like this. So this is the point 1 and e, and this is the point 0 and 1. Okay, and we rotate it about the x-axis, so this is the other side after the rotation. This is what the rotation looks like. And as before, we're going to pick up an element of the arc length. We're going to call it ds. And this element, when you rotate and create a band, okay, and the radius here is y, and the radius is e to the x, because that's what y equals to, and the circumference equals 2 pi y, or 2 pi e to the x. So this is pretty much the setup, and now we need to look at what the heck is ds. And ds will be 1, the square root of 1 plus dy dx squared. So ds, in this case, equals to the square root of 1 plus dy dx squared dx, or 1 plus, and the derivative of e to the x is e to the x. When you square it, e to the 2x, like so. And therefore, now the area, we can conclude that the area will be 2 pi, and this time I will take it out of the integration. The integral, and x goes from 0 to 1 of e to the x times the square root of 1 plus e to the 2x dx. And now I'm asking you wise people to tell me how to proceed from here. And at this point, with the earlier section, there was a lively discussion or debate which technique, which integration technique, or which kind of substitution to use. So, the ball is in your hand. Nicholas, can you close the door? Guys, speak up.
Use substitution for e to the x.
Use the substitution for e to the x. Well, so we have 1 plus u squared. I like that. Actually, this is...
We just do the inside e to the x. Then we take the integral, will be 1 over e to the x. It cancels out e to the x. And then we just have 1 plus e squared, 1 plus e squared.
Okay, what you're saying is, say it loudly. Maybe I can capture it. Say it again.
We have u equals e to the x. Then in the square root, it will be 1 plus u squared. But when we take the derivative of e to the x, it's obviously going to be e to the x dx. And then for substituting in for d, it will be 1 over e to the x. Our e to the x's cancel out, and we're left with 1 plus e squared, 1 plus u squared.
1 plus u squared. And the square root of 1 plus u squared will call for what substitution? Or how we proceed from there? You need to think like a chess game. So what is the next move? Tangent. I absolutely agree with you, and this is the correct substitution. So again, let me repeat for the sake of recording, what Manny said is we'll start by substituting u equals e to the x, and then du will be e to the x dx, which is good because we have e to the x dx, so this will take care of these two terms. After doing so, then e to the 2x is u squared, so we have the square root of 1 plus u squared, and which we have a trigonometric substitution for it, and the substitution will be tangent theta will be 1 plus, tangent theta will be, tangent theta will be 1 plus, no, tangent theta will be u, and we have 1 plus tangent squared, which is the secant squared, so we take the square root of the secant squared, and we get the secant. So we have two moves ahead of us. So let's start with these moves. We're going to first, let's set up u equal to e to the x, and therefore du equals e to the x dx. That's good. As we do so, might as well go ahead and set up the boundaries. I don't think it's at this point it's necessary. Let's not worry about the boundaries right now and proceed from this point. Treat the integral as indefinite integral.
It would just be 1 to e, so it's not like it's...
It will be 1 to the e, I agree.
Probably be a lot nicer than have to do a bunch of that.
Okay, I tell you what. Since you're hot, I'll go with your suggestion. So you suggest go ahead and substitute u now. So, okay, when x equals 0, then u equals 1, and when x equals 1, then u equals e. So we'll go with these boundaries. All right, you talk me into it. So what do we do now? We have a equals, at this point we're looking at 2 pi, the integral from 1 to e of, this becomes square root of 1 plus u squared, right? And e to the x dx is the u. All right, so this was our first move. The next move will do the trick substitution. We're going to say that u equals tangent theta, right? And therefore, du equals secant squared theta d theta, but also 1 plus u squared equals 1 plus tangent squared of theta, which is secant squared of theta. Okay, so the square root of this thing is the square root of secant squared, or simply secant theta. So, and at this point, I'm not going to mess with 1 and e, okay? Because we're going to substitute back to u. So I'll say we have theta 1 and theta 2 here. I'll leave it at that we don't need to determine. So we have a equals 2 pi, the integral, and again, because I don't want to mess with the u to theta substitution, I'll simply say this is from theta 1 to theta 2. As you see later on, it's really, we don't have to worry about it at all. And now, instead of square root of 1 plus u squared, we have secant theta, and instead of du, we have secant squared d theta, and at this point we have 2 pi, the integral from theta 2 to theta, from theta 1 to theta 2 of secant cube theta d theta, which we looked at it yesterday, if you remember, right? So now this we did yesterday, it's a non-integral, and if you look at your note from yesterday, it will be 1/2 secant, the square root is the secant, and du is the secant squared. Okay? So the integral of the secant cube, look at your note from yesterday, was 1/2 secant theta tangent theta. We use the integration by part plus the natural log of the absolute value of secant theta plus tangent theta. Okay? Like so. So we're losing the 1/2 and the 2. We end up having, and this is evaluated from theta 1 to theta 2. Okay? And just one last change, it would be pi times secant times tangent plus the natural log of the absolute value of the secant plus the tangent. Okay, and this is what we take to the next page. Now, we really want to substitute back the secant and the tangent back to u. While we do have already substitution for the tangent, tangent theta is defined as u. So we have u here and we have u here. So let's write in red that this will be the way we're going to bring back. Let's see, where are my color pen? Oh, they're here. I knew I took them out. So this will be, this is u, and this is u. And the secant, if you remember, is 1 plus square root of 1 plus u squared, right? From where did we see it? We saw it right there. The square root of 1 plus u squared is the secant. So we can substitute. So let me change notation here. Let me take off the equal sign and write the following. The tangent by the substitution is u, and the secant from here is the square root of 1 plus u squared. So if we substitute that, we can write the boundaries in terms of u. Okay? So here's what we do the next line. I'm going to bring back here so you can see. By the way, what happens if you don't remember or you don't see it right away, or you have a little less convenient substitution? This is actually back substitution. What's always available to you is the right triangle. Okay? Alternatively, we can use a right triangle substitution. Okay? For instance, we know that by definition, tangent theta is u. So we'll draw a little right triangle, like so, in the first quadrant. Okay? Right triangle. And this is theta. And tangent is opposite over adjacent, so u is u over 1. And therefore, the hypotenuse will be the square root of 1 plus u squared. Right? So we have the tangent. We need a secant. Well, the secant is the hypotenuse over the adjacent, so the secant will be 1, the square root of 1 plus u squared over 1. So right away you can see these two substitutions. So if you don't see it initially, you always can go to the right triangle deal, which is really a wonderful substitution. And now you have pi, and in terms of u, we have the square root of 1 plus u squared times u plus the natural log of the absolute value, again, of the square root of 1 plus u squared plus u. And this is evaluated this time from U1 to U2, and the boundaries on U will be 1 to E. That's why I said we don't have to worry much about replacing or figure out what is the value of theta 1 and what is the value of theta 2, because eventually we'll go back and we do the U substitution. Okay, so let's bring it home. We have pretty much one line to complete the answer, and the answer will be, I'm going to bring U up front here if you don't mind. So we have pi, U is E, so it will be E times the square root of 1 plus UE squared, right? Plus the natural log of the square root of 1 plus E squared again, plus U is E, like so. And then we need to subtract the other result when we evaluate for 1, and then we multiply everything by pi. So when U equals 1, then we have 1 times square root of 2. So we have square root of 2 plus the natural log of square root of 2 plus 1. And we don't need here, okay, this will be inside, so we do need these parentheses. So I tell you what, let me write it minus minus and get rid of one set of parentheses, like so. And we close it, we close the bracket. And that's it, there is nothing to do after that, so let me close the bracket here and box the solution. Okay, again, the reason I don't use absolute value, because everything is positive here. The argument of the natural log is positive, so I'm good here.